Okay, I make a corrections for my yesterday's talk. I gave the irreducible representations for the V group of the real field. In my presentations, I should the L in my mind should be half integer, but in order to be consistent, I will use a different give corrections here. So in this case, the L is in the integer. So the version I used yesterday actually should be the half integer, so I confused myself at that moment. Okay, so that's the correction. And now let's continue today's talk. I will continue to give a summary about how do we use the L factor to characterize the local long-length correspondence. And after that, I will review the Satake transform and to introduce the basic functions. Okay. So in today's talk, I'm going to focus on the non-Archimedean field. Okay. And it takes the O to be the ring of the integers. And fix a uniformizer. And denotes the Q to be the cardinalities of the residue field. Okay, so this is the basic notation I used in my talk. Okay, next let's see. Yesterday we defined the L factors and the the L factors and the epsilon factors for the weight repetition and also the parameters. So I'm going to borrow Wittek's title for one slice, the characterizations of the local long-length correspondence. Okay. So for the representation, we associate some certain invariants, and we use this invariant to characterize this local long-length correspondence. And I will elaborate more. How do we do that? See. Okay, let's take on the general linear group case, which goes from the irreducible admissible representations, goes to the L parameters of the GLN. And we know this is the bijection, and the pi goes to a L parameter. Okay. So this is a bijection. And yesterday we defined the L factors on this side, and also the epsilon factors. And now the question is, how do we define those on the other side? And for the representations of the general linear groups. And actually, we do have the definition, which is given by Goodman-Jacquet. And also, it's able to prove these two local factors are the same. And regarding to the definition on this side, this will be discussed in Julian's talk, so I will skip the details here. But so what we have is we have two families of the local factors, and they are equal to each other. And let me see, for example, what's the mean? We have the definitions for this set, and we associate some invariants according to these representations, the weight representations. For example, in the epsilon factors, you do see the Artin factor show up, and you have this correspondence. And now the natural question is, can we translate the information from one side to the other side? What's the corresponding meaning? So in this case, we have a arting conductor here. And now the next question is, what's the corresponding invariance on the other side? We actually also have the conductors for the repetitions. Both of them give you the non-negative integers. And let's recall what is the conductor for the repetition, the irreducible repetition of the GLN. So if the conductor is 0, which means this pi is unramified repetition. And which, in other words, the pi has a maximal compact invariant vectors. Okay, let's see the second case. The conductor is greater than 0. And in this case, the conductor means the smallest integer smallest integer such that some compact group invariant subspace is not zero space. So let me specify what is this compact subgroup. Okay, so this is the subgroup we are looking for. This is the integer pointers for the GLN. And we have the last row, the C and D. The C is a row vector of dimension n-1. So this is the constraints. And also we have the D is equal to 1 modulo pi T O. Okay, so that's the compact subgroups. And also we notice the arting conductor is the whole epsilon factor is depending on the psi and also the Howard measure we used. So in order to nail down this equation, I need to assume the phi of conductor O. And also, of course, the psi is not too trivial. And also, we fix the Howard measure. Is the volume have 1. So that's the assumptions on the normalizations for the Howard measure and the additive characters. After we choose these two, and we're going to have the conductors, these two conductors that match. And this is how do we translate the informations for the local Laurentz correspondence. Okay, this is only one piece of the information. Of course, you also have the local root number, but I didn't give precise formulas for the local root number because it's way too complicated. It's a highly non-abelian Gauss sums. So in general, we don't have formulas for that, for the local root number. Okay, so this is the correspondence of the invariance. And also let's see how do we use those L factors and also the epsilon factors to characterize this local Laurentz correspondence. Let me give you examples for the GL2 case. Okay, before I split out the conditions for the L, for the local lines correspondence, and let's go back to look at these two sides again. And for this case, we want to match these local factors, and we have the equations like this. And in the last lecture, we already see the most cases, if you have the phi is irreducible, the degree is higher. And when the pi is the supercuspidal representations, and we know this L function is equal to 1. You have infinite many supercuspidals, but all of them share the exactly same L factors, which is 1. And the epsilon factor is more complicated, but it's still, when you have the bigger n, you could have two different supercuspidal representation. They have the exactly same epsilon factors. So which means you have this map, if you only use this necessary, this is give you, you want to match the local factors, give you a necessary condition, but this is not sufficient, which means I can artificially give an arbitrary map from this side to the other, to the L parameter side, and they also have the same L functions and the epsilon factors, but it's possibly not so-called the canonical choice if we only look at this, if we only have these conditions. Okay, so we need to add more, and to do that, so let's twist a little bit. So instead of only consider the GL2's L factors, we twist with the character chi. Okay, we let the L factors or epsilon factors on the both sides equal to each other. They are equal for all the characters. Okay. So if this equation is true, for all the chi, and this is going to give us a unique map. So then in this case, this map is going to be determinant, I mean. Okay. Okay, now let's see why we need to twist this GL1. The one reason, of course, you have the converse theorems that can help us to determine this is going to give us the unique map. And another point of view to look at this is using the long-lines functionality. Okay, now let's see a general pictures here. I still stick on the connected split reductive group. Of course, this is defined over F. Okay, and in this case, we start from the irreducible representations of G. And we know this is the local lines tells us this is going to give us a finite to one map goes to the L parameters. Okay. So this is a split case, so I only consider the complex dual and ignore the Galois set. And we can consider arbitrary representations from this the arbitrary complex representation for the dual group. Let's put a row here. And this is going to give us map to the GLN C. Okay. And if we compose this map, we get L parameters for the GLN, the capital N. And if we look at now, we also have the local lines correspondence for the GLN, and this gives us a bijection. So if we have L parameters for the GLN, you're going to get a unique irreducible representations for the GLN. So we have a lifting map from the irreducible representation of the split reductive group goes to the representation of the GLN. So let's denote this lift is L rho, which is depending on the rho. Okay, so this is pi. And based on the definition, it's easy to see the gamma factor we defined for this pi associated to this rho is equal to the gamma factor we have for this representation of the GLN. So by that, I mean the following. Okay. So you see the first line we have here. I combine everything into this gamma factor because the gamma factor contains both L factor and the epsilon factor. So we actually assume this actually we know this is true for all the L and the epsilon, but here I just focus on the gamma factors. So all this on the first row here, we have everything is on the L parameter side. So this is the parameter of GLN. This is how we define it for the general G and rho. And if you look at these two rows, these columns, this is what we just get from the local lines correspondence for the GLN. So in other words, this set is given by Goldman-Jacquet. And now our question is how do we define a gamma factor associated to this pi and which is compatible with this lifting? Okay, so this is our question. And on the other side, let's look at this picture. This is another way to understanding this theorem is by looking at this is the representation of the GL2, and this chi is a representation of the GL1. So what we matched here is actually we match the L factors or the local factors for the GL2 cross GL1. So it's not just the one group. It's a tensor product of the two groups. So in this case, we are thinking this G as a GL2 cross GL1. And the rho will be our tensor group. So that is help us to nail down, and using the converse theorems can help us to nail down this map is unique. So this is one idea to using the L factor to characterize the local line correspondence. And for the representation theoretical side, this is the part we missed, like the general version of the Goldman-Jacquet, the integral. And in Zhiling's talk, he will, in the next week, all his 5 talks will be scheduled in the next week. So in the next week, he will discuss Braverman-Kazhdan-Ngo's proposal, how to give a general framework setting to define this gamma. Okay. And also, of course, to leading that, he also will recall the Goodman-Jacques result. Okay, this is a summary for my last talk and also elaborate more details on the characterizations. So the next two, I'm going to recall the Satake transform and define the basic functions. Okay, before that, I'm going to go over the Euro notations. Still the G is a connected speed reductive group and a fixed B to be a Borel subgroup. And of course, this is also defined over F. Everything is defined over F. And T is the maximal speed torus. Okay. This leaves us the U to be the unipotent radical. The GM is referring to the GL1, the multiplicativity group. And this is give us the characters, the set of the characters, and also the set of the co-characters. And between them, we have a duality pairing. Okay. And we choose the K to be the maximal compact subgroup. Also, it's just the hyperspecial one, but it's easier way is we just take the integral point. Okay, and now this is, I will use this notation, and later on I probably will not recall it again. This is the Euro notations we have for the algebra group. Okay, to review let's start from the hack algebra first. Okay, for the hack algebra, the element is just the k-bar invariant locally constant function, which is compact support, and the multiplication is the functional convolution. So, for example, what is convolution? Convolution. I'm going to go to there. Oh, yeah, this is X. Okay, yeah, the Euro convolution. Okay, it's just to specify the multiplications here. Okay, now about this algebra, about this hack algebra, let's see the element is we have the k-bar invariant. We apply the Cartan decomposition. So we got disjoint unions, the partitions for the GF. And it's here, the mu is going to run over in the dominant co-characters. Okay, so we have this Cartan decomposition, and the delta, of course, is the set of the simple roots. So if we apply the Cartan decompositions, it's very easy to write down a basis for this hack algebra. So it's going to be just the characteristic functions over every coset, every double coset. So I'm going to use this one for the characteristic function instead of the trivial representation. Okay, so this is, we have a basis for this hack algebra now. And if you use the convolution to calculate the multiplications, the convolutions of the two characteristic functions, and you will see they are commutative. So this is give us a commutative algebra. And this is only very rough information. Now let's just go deeper and to see what is the algebraic structures for this hack algebra. And to do that, let's recall the Satake transform. Okay. We take a function, the k by invariant function, and integral over the unipotent part, and this is going to give us a function in the hack algebra over T. And the maximal compact group we take here is the TO, which is the intersection with the K. Okay, and here the delta B is just the modulo characters for the Borel. And now this is not done yet. Let's look at the right-hand side first. This hack algebra over T. The multiplication over T is commutative, so the algebra here is very easy to figure out. And now let's see, we consider the hack algebra over T is defined, essentially defined over those cosets. And we have a very natural map from here, goes to the co-characters. Okay. And let me show you the map we used here. So I put an element in this coset, and we can define a co-character, gamma T, such that the gamma T takes the inner product with all the chi is equal to the order of the values. So the order is the order for the periodic group, periodic field. And here, this is for all the chi. For all the characters of the t. So we are looking for the image for the t, this gamma t, which is the co-character. And I want the co-character, this is the fixed co-character, takes the pairing with this, all the chi's is equal to the valuations. So that is, this is going to give us an isomorphism map. Okay. And also, in the VTEX talk, when we introduce the dual group, we know these characters of the co-characters of the T is can be identified to the characters of the dual groups. So the T hat is from the dual group, the dual side. And in the rest of my talk, actually, I'm going to abuse my notations and consider the image here could be here, could be in this hack algebra, and also it could be considered as a character. In the other kind, could be a weight for the torus, and also could be a co-characters. So I'm going to abuse this, but I will explain the content. And this is one refinement for the image. I mean, one interpretation for the image. And also, we have this Sasaki parameter actually is adjoint invariant, which means let's just recall one formula due to Harshchandra. Okay, now the T is just the split torus, and this formula is also can be considered as the example in the Apkshi's talk. And this is also an orbital integral for the split torus case. And for the test function f we take here is from hack algebra. Okay, and here the dt is the discriminant. Here the U actually is the Lie algebra of the unipotent part. Okay, if we use the Harshchandra result here, and we can see the image actually should be the well group invariant. The well group is normalized the T. So we got T is which part, sorry? T is why this is vanished? This one? Sorry, I didn't get here. Okay. T should be regular? Oh yeah. Oh, I mean, yeah. T should be regular. Right. This is not the. Okay, sorry. It's not the split case. Yeah. Okay. Right. Yeah. It should be the regular part. Sorry. yeah, maybe, okay, sorry. I probably just not recall this one. It's not make my point clear. Sorry, let me just use. Sorry? Yeah. Yeah, I think it's just to make my point more complicated here. I only want to lead into the Satake isomorphism, so probably I don't need this anyway. Sorry. Okay. So, Okay, so my point is leading to say this image is not just the arbitrary element here, it also should be the well group invariant. So that will be we're going to have an isomorphism for the hack algebra. Here the W is referring to the well group. And if we identify the axis, the co-character to be the character over the dual set, this is also, they share the same well groups. So I'm going to use the same W here. Okay, so this is the structures of the hack algebra. And now let's give an example. For example, we have a basis for the hack algebra, which is the characteristic functions over the coset right here. So we have those bases. So what happens if we plug in those basis vector? What happens if we plug in those bases instead of the Satake parameters? So what we will have So this is the basis is parameterized by the dominant co-characters here. So I'm going to pick up one element from this set. Okay. And so what we're going to get is if we use this set, if we use this identify the image to be the W invariant over the characters of the T hat, the dual group. So we're going to get linear combinations of the characters of the representation. So let me just specify here. And here this rho B is the sum of the half of the sum of the positive roots. Okay, and this part, the A lambda mu is a integer. So this is the integral linear combination. The chi lambda is just the character, the weak characters of the irreducible representation of the dual group. This is a complex group, and the associated hashed weight is the lambda. Okay, so that is our characters. And the Satake transforms for this characteristic function is just the integral linear combinations of all the mu, which is the mu is also stated in the dominant co-characters. So the mu is also belongs to x plus star t, which is less or equal to the lambda. And from this side, it's also easy to see this all the chi lambda and chi mu, they are the W invariant. Okay, so this is this is what's the Satake parameters for the character for this function. And because this is the linear relations, you also can take do the inversion to find to write down this chi lambda in terms of the linear combinations of the Satake transform. And this is one special case of the Cato's general theorem. So we write down this chi lambda in terms of this is a Kazhdan-Ngo polynomial, and this is our Satake transform of the basis. Okay. And this is one version if we use the Kazhdan-Ngo polynomial. Another version is we can use the Lustig's Q analog of the Constant's partition functions. We can have a different version. So it's just to do a substitutions here. Okay. Later on, if we still have time, I will recall the details of the definitions for the Kazhdan-Ngo polynomial and also the analogy of the cosine partition functions. Before that, let's just move to define the basic function. Okay, so this is just a summary for the hack algebra and what's the image for the Satake transform. Mm-hmm. Yeah. Right. Oh, here I use the version which is we like the. I'm gonna switch the Q to be the Q inverse here. Just a simple substitutions. So let me just. Yeah, I'm gonna keep this for a few minutes and come back to this later when we apply into the L functions. Okay. So next, let's see the unramified representations. Okay. And for the, let's see how do we connect it to the unramified representations here. Before that, let's see how do we associate the every representation as a Schwarz space module. So let's take a pi to be an irreducible admissible representation. Okay, so this is, we define the F is acting on the vectors inside of the V. And because in this case we have the pi is admissible, so the image of this operator, so this gives us an operator on the V, no matter what compact support function you plug in here. And since the representation is admissible, so the image is going to be the finite dimension. So it makes sense we take the trace of the image. And this is going to give us the G-adjoint linear forms on this Schwarz space. And now let's specify to the unramified representations and also the Hecke algebra. If we take the F is from the Hecke algebra, which means we take it as a Biking invariant function. And in this case, if we consider the operators pi f acting on the vectors in the representation, so the images always give us a k-invariant vectors. So if we take the v is k fixed, for example, we take a v is the spherical vectors, and we know this space is going to dimensional 1. This is unramified representation. And if we pick up the v's here, this v is going to be exactly the eigen functions, the eigenvectors in this case. So we're going to have a eigenvalue, which is our eigenfunction times v. And this now you can run over the choices for the f, and we're going to have the omega f give us a algebraic homomorphism for the Hecke algebra. And now let's give a formula. It's not hard to check the omega f is the integral of the Satake transform with the character associated to define the unramified representation pi. So let's just denote by theta. And theta is the unramified characters on the torus. So we have an induced representation, and the pi is unramified constituents here. And also this theta going to give us the Satake parameters, which is the L parameters, the image of the Frobenius element. We know for this unramified representation, the L parameter, which is trivial on the SL2 part, and is also trivial on the initial part. So it's only determined by the image of the Frobenius element, and which give us a semi-simple conjugacy class in the G check in the dual group. So in this case, it's also determined by this theta, the unramified character. So this is a semi-simple conjugacy class of G check. Okay. And now, if we thinking this image is the character, we know this image is living in the Hecke algebra over the torus. So this gives us the characteristic functions over T, modulo the integral points. And integral with this theta is basically, you just apply this theta into these characteristic functions. And now let's see, if we calculate the trace, in this case, the image of this V goes to the V is the eigen vectors here. So if you calculate the trace, we just take these coefficients here. And so we have the trace is equal to this omega f, and we calculate here, and this theta is give us the Satake parameter. This theta is corresponding to the Satake parameters. So if we take the compositions, this is the values for the omega f, and in other words, it also gives the trace of the path. Okay, and in this case, we also can think in this is a semi-simple conjugate class in the G hat, which is in the T hat, in the dual of the T, the torus, and this is give us characters of. My point is this belongs to T hat, and this is belongs to the characters of the T hat. So this is we evaluated the character over this semi-simple conjugacy class. So that is give us the trace. Okay. Okay, so now we have a formula here. Sorry? Is only, I only consider the Hecke algebras here. The F is the Hecke algebra. Yeah, linear combination, yes. So we have the Satake, right. This is the linear combination of the characters. Okay. Now this is a linear combination of the characters. If we take the values, this is basically the polynomials of those elements in the C pi. And now let's see how do we use this to get the L function. I mean, we can replace this F by a general function, not just limited to the compact support functions here. Okay, we can enlarge our choice to plug in the different F. and trying to using this polynomial to become a formal series. And if we have a formal series, and we're going to get the unramified L factors. So that is our goal. Okay. So to do that, I'm going to put the constraints on the G. And later on, I will explain why we need those extra assumptions. Okay, this is relating to the row unramified L factors L as pi row. And to do that, I have first is the constraints for the reductive groups. And we have this is not, we assume the G satisfies this short exact sequence. And this GM is just the GL1. And we default this to be our determinant map. And also, we assume the T0 is the maximal speed torus for the G0, and the T is as usual, and this is the same GM part. And we assume this co-characters also have this short exact sequence. So this is our condition put on the G. And the last part is the constraints for the row. The row is the complex representations for the dual side. So we have the G check goes to the GLV. This is complex GL. And we have in the dual set, we're going to have a dual short exact sequence for this one. And then you're going to have embedding is the GL. This is basically C cross embedding to the G check. So for this C cross, the map is just the scalar multiplications. So that's the constraints for these complex representations. Sorry? The G naught, so far, later on, for n semi-simple simply connected, the Gauchois has a recipe from the G0 to construct the G. So, but in this part, I don't need that at the moment. So I only need these three constraints to produce the basic functions. Okay. Yeah.
Start with row.
Yeah. It means the last one, then go back to construct. Yeah. Okay. Yeah, I can do it next time to following Gauchois' paper to construct the G. Okay. So now I have a G here. I'm going to stick on this G and this row. So and also still again assume the pi is the unramified representations for the G. So the goal is to study this unramified L function. And so the point is we are trying to define the basic function. And if we use this basic function to replace this test function f, and we expect to get the L factors. So this is our goal. And in order to do that is the point is that we do the expansions for the L factors and then apply the inverse of the Satake transform. So it seems that I'm going too slow this time, so I probably will leave already run out my time. So I'm gonna stop here and to calculate how do we construct this L in the next, how do we construct this basic function next time.